I want to stick with this slide a little bit longer to make another point about things that are ortho-para-directing. It's not only just the methyl group that forms particularly stable carbocations when you have substituents at the ortho or para position. What I've drawn there to the right is the intermediate for phenol with the OH group at the top of the ring, and that's in the process of adding a nitro group that's ortho to itself. And you'll notice that OH groups are towards the top of that list in the table on the last page of these notes, strongly activating, even more so than methyl groups. That must mean that they can form particularly stable carbocation intermediates, even more stable than a tertiary carbocation. And what I have here over on the right here, I guess you wouldn't say that's a tertiary carbocation. The positive charge is on a carbon that has two other carbons and that oxygen attached to it, but that's not quite the same as saying it's tertiary. What's special about that structure, though, is what it can lead to if we take two of those electrons off of the oxygen and reassign them to form a double bond, like I'm implying with that blue arrow there. So the result of moving those two electrons off of that oxygen, our OH group still has one pair of electrons on it, but now we've got a double bond to the ring, and everything else stays the same. We've still got our NO2 group over here. We've still got the hydrogen there. If you calculate formal charges, there would be a positive charge on that oxygen now. So we've moved the positive charge from the carbon up to the oxygen. But this is a more stable structure that I've drawn because now the octet rule is satisfied for all the carbons in the ring as well as for that oxygen, even though it does bear that positive formal charge. And if we can draw an octet rule structure for all the atoms that want an octet, the carbons and that oxygen, that is particularly stabilizing. That gets 2 exclamation points. That's even better than a tertiary carbocation. And so you find that you can draw such a structure if you are in the process of adding the nitro group either in the ortho position like I'm illustrating here, or you can imagine if it's a para substitution, again where you can get that positive charge up at the top of the ring, and if that was an OH group here instead of a CH3 group, then I could draw something that's similar to what I did with the octet rule. We can get an octet rule structure from that as well. With meta, again, the meta arrangement does not get that positive charge at the top of the ring. It wouldn't get it close enough to that methyl group for it to be stabilized, and if there were an OH group, meta substitution would not allow me to draw an octet rule structure like I just did there. So for things, like I say, that have those pairs of electrons that are available to do that, make that double bond, they are particularly able to form stable structures if there's an ortho or para arrangement going on. If I skip down to this, this is the last slide in the notes, and you'll notice here that NH2 is right at the top of the ring, very activating, ortho-para directing, and they're highlighting pairs of electrons that would be able to donate themselves to that ring in order to form that double bond and again eliminate the carbocation altogether. We say that these are electron donating groups, and so they're towards the top of our list here of things that are very activating and love to make ortho and para products. The R here, by the way, represents alkyl groups in general. So again, more reactive than benzene, but not as reactive as, say, the OH group in phenol. Again, the more stable we can make that intermediate, the faster it's going to form, and so we get good high reaction rates.